So last time, Monday, we've been through the basic introductions of these second order systems, and this is the second order system. And from the handouts I give to you last time, you can take that handout with you. Okay, so that is the formulation for this, and so this is the solutions of the second order systems to unit step input, and this is the if we using numerical simulation, we can draw the different curves per different value of the zeta. Okay, and then we scale to the omega n, so that is a response. And by either way, maybe you can look at, say, for example, we look at this curve. This curve corresponding is zeta equal to 0.3. So we try to get certain feeling about the oscillation. So basically, this oscillation is going to oscillate. Our command is equal to 1 because we are trying to follow the unit step input. So this level is our desired. We want to achieve the output to this level, which is equal to 1. So you can see when the damping ratio, the system with small damping ratio is going to overshoot. But again, because the system is closed loop, so the closed loop mechanism will try to bring the overshoots back. But for some reason, it's given too much power, so bring back too much. So go down a little bit, okay, and now the system, again, in the feedback loop, it tries to pick it up, and by providing more, okay, so now for the second overshoot is much smaller than the first one. And so this kind of oscillating until eventually reaching to the level of 1, okay? And as long as you make the system in the negative feedback loop, the system will eventually converge to a certain level, okay? So that's the features. And with this one in mind, then I will begin to talk about how to characterize these systems. So here I simply pick up one typical example. Say this is the damping ratio, for example, 0.3 or 0.4, 0.2, whatever. Okay. So this is the solutions, and this is the transfer functions to original closed loop system, and that is what we define here. So this is the systems we're talking about. If you remember, so that is the systems omega n squared and s times s plus 2 zeta omega n. We consider this particular systems and we put into unitary feedback. So this is the input, this is the output. So this is a particular system we picked up for introducing this concept. And this one we study is y over r is equal to, there we included. We want to know is what is the response of y corresponding to that transfer function multiplied with r, and here the rt equal to the unit step input. So that is t, and this is 1. So that means rs equal to 1 over s. Okay, so basically with the r of s and multiply with that transfer functions, then we resolve and we're taking up the y of t by taking up the Laplace inverse of transform of this transfer function multiplied with s. So that is the whole page procedures. This one appeared in one handout I give to you. So that one come up with the result of yt is equal to this equation here. Okay. So if we have the numbers, then doing this calculation shouldn't be hard. But here is more generic. Okay, so that is 1. From here you can see 1 is our command. Okay, that is the value we try to achieve. And somehow for the yt, the output response is superposed to the desired input with certain oscillations. Okay, the oscillation is in sinusoidal oscillations, and the oscillation frequency is given by this value here. Those are the features I try to highlight to you. Okay. In addition, the magnitude of the oscillation is governed by this value, and this value in turn is an exponentially decay. So that means here you can see basically the output is the superposition of 1 plus certain perturbations. The perturbation is in oscillations, and the oscillation is decaying. This perturbation is oscillation in the fixed constant of the frequency, and in the fixed constant frequency vibrations, and also in decaying. So basically that is the features here. Okay, so if you have the highlight markers, you should highlight this term. That is tell you the frequencies of the perturbation oscillations, and highlight this whole term that tell you the magnitude of the oscillations, which is in this feature in decaying. Okay. And so that is the things here we can do. And with this one in mind, then we can begin to talk about the characteristics. Let me see the next page. Okay. Here I try to follow up our textbook content, and those ones we can talk about before, but let me quickly go over it again. So basically here depends on the characteristic equation. This is our characteristic equations here. So from the characteristic equations we can solve for poles, okay? So basically the poles is this. So our characteristic equations is S squared plus 2 zeta omega n s plus omega n squared equal to 0. So its root or that is called the poles of the system. Okay, of the closed loop system. Basically here that is S minus this one. So here we have the real part and we have imaginary part. And we discussed this before. Depends on the location of the real part, imaginary part, then the behavior of the response can be correlated. And that one, again, here I summarized to a few pages in the following. And so here, what is beta? So beta basically can be determined by this. So here, let me plot this is the real complex, and this is imagined. So this is called the complex plane. Okay, so if we plot the complex number, so for example, say we have a complex conjugate, so that is the location of the two poles here. So corresponding is the real part has the magnitude is given to is minus zeta omega n. So that means from here, this is the minus zeta omega n, certain negative number. And the imaginary part is given by that one, that is here omega n times 1 minus zeta squared. Okay. So we have this one, then I want to answer what is that angle. So that angle is very straightforward. So by linking this line from the location of one pole to the origin here, then if you try to look up this triangle, and from there you can get a clue about the angle there. So let me draw the angle. Let me draw the triangle here. For this triangle, we have this side is zeta omega n, I mean the magnitude, okay? And this side, we have the magnitude omega n, 1 minus zeta squared. So this angle, the symbol there we're using is called the beta. So from here, can you see the beta is many ways we can express beta. So first of all, by taking the square root of the square terms here, basically this one you can quickly determine that is called the omega n. Okay, so therefore from here, cosine beta can be equal to omega n zeta omega n, right? So therefore beta equal to a cosine of zeta. So this angle is highly correlated to the damping ratio. The smaller the zeta, we can calculate what is zeta is. What is cosine? Cosine is something like this. Okay, so sorry, cosine beta here. So this one, basically here you can see so how can we get it feeling? So the way you can see is this: when there is no damping ratio, basically this one will give you the damping ratio equal to 0. This will give you a value is how much? 90 degrees. Okay, so that means let me give you a certain scenario here. So that is the real S, imaginary S here. So for system with very small damping ratio, basically is the poles is something like this. It's very close. It's very close to the imaginary part. Okay. And for the system with a very large damping ratio, so for example here we have the system like this. So if the damping ratio is close to 1, then basically beta is close to 0. Okay, so that is a system we have the damping ratio something like this. So basically this one corresponding is the systems with large damping ratio. Okay, so for the green one, that is corresponding very close to imaginary. Imaginary, that is the systems with small damping ratio. Okay, so that is the feeling about building up the relation between the location of the poles to the complex plane. And this page, again, is to summarize how the system is stable or unstable. As long as the poles on the left hand side, then the response corresponding will be something like this. Those are showing a schematic drawing, and those things you can see either they will converge to a certain value, or they will be oscillating but will be decaying again, converge to the certain value. As long as those poles on the left hand side, they will be stable. Stable, that means eventually the system is going to converge to a certain value. And why is this? This explanation, this can be explained by this. The system, the poles have the real part and imaginary part. The real part is this value. This value is exactly equal to exponent the coefficient of this. So as long as pole is on the left-hand side, this portion is always negative. In other words, as long as the pole is on the left-hand side, then the exponent coefficient, the constant, is negative. It will be decaying. On the other side, if the real part of the pole is positive, that means the whole terms, this coefficient will be become positive. Become positive, then of course this one will be exponent growing. So that reason we can explain to correlate. So for the two cases, they have a positive, the real part, then basically the system will diverge from the desired value here. Okay, and for this case particularly, this has damping ratio equal to 0. That means the real part equal to 0. Then again, we'll look at the solution here. The solution of the here. The real part equal to 0. And what is the real part? The real part is this. Okay, when this equal to 0, what that means? That means this exponent, this coefficient equal to 0. So that means the whole coefficient here become 1. So that means the result will be 1 minus a pure sinusoidal oscillation. So that means the system will oscillate without the magnitude without decaying. So that is come to this case. Okay? So that is the way we can correlate these things. And this one we done before, so I went over this one quickly. So this page and give you another view of the systems. And for this case, again, this one pretty much summarized. I talked about that before. For this system, the system with damping ratio zeta 1, that has a large angle, and this one system has the smaller angle here. So basically, by looking at by comparing the angles, again, if you remember what I made a note here, for the system with smaller damping ratio, is poles is more closer to imaginary axis. So from here, the system with smaller damping ratio is closer to the imaginary axis. So of course, zeta 1 is smaller, zeta 2 is larger. Okay. And for this case basically is saying, let me make one case here. So again, we can compare. So this is a complex plane, okay? And here we have two systems. One system is, for example, here. Okay, so let me using the same damping ratio. The other system is here. For the both systems, you can see they have the same angle, which means they have the same damping ratio. But the two systems, this one is, let me call the omega n1. And for the second system from here to here, let me call the omega n2. I mean the magnitude from the origin to there. Okay. The comparison of the systems, their dynamic response, let me draw that here. Basically, you can see the black system, it has a smaller value of the omega, which means it has a smaller value of the oscillations. So when we draw in the time domain, the black system will be oscillating in these frequencies compared to the green one. Okay, for the green one, it from peak to peak, it has a shorter period. That means oscillation is in more frequencies. And for the black one, it has a larger period. That means oscillation frequency is slower. Okay, using this graph and basically explain this. So for the omega n1, that has oscillating in slower compared to omega n2, and then the omega n3 that has oscillating the fastest one. Okay. So again, this is the summary for this. That is another thing, and so basically that tells us is how fast we can oscillate. And again, from the real part, for example, if we have a system, say the real part one is -1, the other one is -10. So how they compare? So you can see the real part, again, is the coefficient of the exponent function here. Exponent minus t compared to exponent minus 10t. Which one decays faster? This one. Alpha 2, for example, minus 10 is decaying faster than, for example, alpha 1 is the minus 1 here. So that is the effect of the location of the real part there. Okay. So combining, basically, this single equation can explain, cover, include everything, and those things simply is a graphical representation of the individual scenarios. So I think today I haven't really gone through. So those ones for your reference. And Monday we will start from here and then bring your handout. We will begin to do quantification of those performance. And I just post homework 4. Suppose we need to have a homework 3 first, but homework 3 is for steady state error. That should be the next section. So I post the homework 4 first. And that one, once we starting from Monday, then you should be get ready for the homework 4. And that one, I believe the due is about 10 days from today, so you should have plenty of time.